What questions do you have? Questions at all? Things going okay? I did move some of the due dates for WebAssign homework. It'll be reflected in WebAssign. In particular, there was a WebAssign assignment that was originally due tomorrow. It's now due on Sunday because we're finishing up 3.2 today. So I moved that and shifted 3, 3, 3, 4, and 3, 5 accordingly.
So we're gonna have 2 assignments due on Sunday?
No, I moved that one.
Okay.
Yeah.
Okay.
Yeah, I moved the 3 to Sunday, and then I shifted the 3 to Tuesday, and I moved them all.
Okay.
So there's no day in which 2 assignments are due. So
Okay.
yeah, I shifted them all. So I thought I'd let you know that. So your 3-2 homework will be due on Sunday. Okay, we're gonna finish that up today. We'll get into 3-3 today. Probably won't finish 3-3 today. We'll get that finished on Friday and start 3-4. So in any event, let's finish up this problem we were talking about at the end of class last time, and then do one more example like that before we get into trying to reverse the process of what we have right now a little bit. So looking at this example, notice that we've already got some of the answers from last time. We've got this polynomial, it's factored for us, and then once we have it factored, we notice that we can answer a bunch of questions and get a little bit of better information about what the graph has to look like. But notice I gave it to you that's in factored form. If you look ahead to the next problem, it's also in factored form. So what we're going to be doing going forward past today is if we have a polynomial that's not in factored form to start with, how do we get it there? And so that's where we're headed with this stuff. So like I said, reversing this, I'm not really reversing it, but trying to get us to this point and then be able to answer these types of questions. So that's where we're headed with all of this. All right. So last time we answered these questions, remember the degree here, the quick way to do that is if I've already got it in factored form like this, we can just look at the exponents that are on each of the factors, right? If you multiply this out, you'd have an x squared term. If you multiplied this out, you get an x cubed term. So if I multiplied everything out, you'd have an x squared here times an x, which would give you an x cubed, times an x cubed, which would give you x to the 6th, and then times an x would give you x to the 7th. So that was where we got the degree of 7 from, right? Talked about that last time. The leading coefficient, remember that's the coefficient on the highest degree term. Well, we just went through all of that explanation. This would be a 1x squared when you multiplied it out. There's a 1x here, 1x cubed, and 1x, right? So the only thing that's going to get multiplied by is this -3 in front. So that was why the leading coefficient was -3. Just remind me of where we came up with those numbers last time, since we are splitting this over 2 days. All right. So the reason why we care about degree and leading coefficient is because that gives us the end behavior. So degree being odd tells us that the tails either, do they point both the same direction or opposite direction? Opposite when it's odd, right? So this negative, you go lower left to upper right or vice versa? Vice versa, it goes this way, right? So again, this is just a symbol description of what we just said there. We said we went from upper left to lower right. So this says as you go to the left, the function goes up to infinity. As you go to the right, the function goes down to -infinity. So we filled that out last time. And we'll have another example of filling that out here in a minute. Is that a good reminder of what we did last time? Okay, cool. All right, y-intercept. We talked about how to find this last time as well. How do you find a y-intercept? What does the x-coordinate have to be if it's the y-intercept? 0. So to find the y-intercept, we need to compute what? What do we do to find the y-intercept? Yeah, we need f of 0. Exactly. We're going to replace this x with 0. If I replace the x with 0, I get a 4 squared for that first factor, just a 1 for the second factor, a -3 cubed for the third factor, and a -5 for that fourth factor. Right? Because I'm just putting 0 in for x. What do you get when you multiply all those numbers together? Bless you. Somebody has to have a calculator. I'm not doing that in my head, sorry. Oh my goodness. Bless you. Is that what others got? Okay, cool, good. I didn't say it. It's a big number, so I said I'm not doing that in my head. That was why you have the calculator. You can do that. Okay. Is that what others got? -64. So let's see, it should be positive or negative. Let's start there. Negative, when you do a cube of negative, you'll get a negative. So that's going to make it positive times another negative. It should be negative when we're done. All right, cool. Like I said, when we do a rough sketch, we're not going to draw this to scale, right? I'm not going to try to scale down to -6480. Okay. All right. How about x-intercepts? What do we look at for the x-intercepts? Yeah, when the function's equal to 0, right? We want f of x equals 0, and this is why the factored form helps us. When we set it equal to 0, this is already factored. If you have a product of two things or multiple things that equals 0, what has to be true? If two things multiply together to give you 0, what has to be true? One of them is 0, right? So I've got a product of 4 things, well, technically 5 things here. I've got a product of 4 things here that's 0, so one of them has to be 0, right? Okay. So what makes the first factor 0? -4. What makes the second factor 0? -1. The third factor 3, and the fourth factor 5. Yeah. So technically, we should be writing each of these answers as points, since it's asking for intercepts, and intercepts are points. So since we came up with f of 0 is -6480, what point does that tell us is on the graph? Good. Yeah, 0 comma the -6480, right? That's what it means to be a y-intercept. The x-coordinate is 0. The y-coordinate is where it crosses the y-axis. What about the x-intercepts? What would the points that have to be on the graph here? Good. Again, intercepts are points. We describe points with ordered pairs. So if it asks you for a y-intercept or an x-intercept, you should be writing it as ordered pairs, or at least when I ask it. Depends on what letter sign wants to accept, I suppose, for the homework. But when we're talking about intercepts are points. And I want to make sure that we emphasize that these are points on the graph of the function. So write them that way. So far, so good? All right. So remember, the intercepts and the zeros go together, right? So the zeros of our function are these 4 x values that we just found. What do we look at to figure out the multiplicities of each of those zeros? What piece of information is this asking us for? Yeah, the powers of on the factors that those came from, right? So for x equal to -4, the multiplicity is what? Good. For x equal to -1, what's the multiplicity? 1, good. There's a power on the x here is a understood 1, right? Up there at the top. For x equal to 3, it's 3. And for x equal to 5, the multiplicity is 1. Again, that's just the power on the factor that gave us that 0. The x, for example, the x equal to 3 came from the x minus 3 factor that has a power of 3 on it, so that's where that multiplicity comes from. The x plus 4 is where the x equals negative 4 came from. It has a power of 2 on there, so that's multiplicity is 2. So it's literally just the powers that are on the factors. So far, so good? Okay. There's two things that the multiplicity tells us. The first one is whether or not the graph flattens. What about the multiplicity tells you whether or not the graph flattens? We talked about that last time. If it's greater than 1, it flattens, right? So where are the multiplicities greater than 1? It's not a trick question. Where are the multiplicities greater than 1? Yeah, the 2 and the 3, right? So where are the zeros that it flattens? Not a trick question. Yeah, -4 and 3, right? Those are where the multiplicities are greater than 1. Okay. All right, so now we want to use all of this information that we found plus one more piece of information to help us get a graph of this function. So the first thing we're going to do is we're going to plot all of the points that we have. There's an x-intercept at -4. There's an x-intercept at -1, 1 at 3, and 1 at 5. So I will put the scale on my x-axis because I can do that pretty easily. I'm not going to scale my y-axis. However, I am going to mark one point. We said that it crossed the y-axis at -6,480. Way down there. Right? So far, so good? Okay. So all I did here was just label the 5 points that we have. Now we're going to get ready to draw the graph. From the end behavior, do I want to start on the upper left or the lower left from the end behavior that we talked about? Upper left, right? So I'm going to come down from the upper left. And what happens at -4? Well, we just said a second ago it flattened, right? So I'm going to make it flatten out at that 0. And then this is the last piece of information that the multiplicity tells us. Does the graph flatten out and cross? Or does it flatten out and turn around? Does it cross or kiss the x-axis right there? Does it just cross it or just touch it? Yeah, so I've heard both. What tells you about, we look at the multiplicity. What is the multiplicity for that 0? 2, which is even. So when it's an even multiplicity, it just touches, right? So it's going to turn around and bounce off. Okay. So I know it's going to go down, and turn around and go back up again. Now I have to go through this 0. Now what about this 0? Does it flatten at this 0? No, and it just crosses straight through it, doesn't it? No flatten. It's just going to go down and cross. Oops, didn't label that point. And I know that we also go down through that y-intercept, don't I, next? We need to turn around, go back up. What about 3? Does it flatten? Yes, it flattens. Does it cross or touch? Crosses because it's odd, right? So I got to go up. I need to make it flat. but I still need to go up. Okay. It looks like x cubed, right? Remember x cubed looks like this, right? We want to make that kind of shape. At least make it bend somewhat. I didn't make it very flat myself. But it should go up, flatten, and turn around again. Okay? It's going to cross because it's odd. It flattens because it's bigger than 1. Finally, we need to go through that last point. Does it flatten on the last one? No, because I have the list of where it flattens up here, don't I? And does it cross or touch? It has to cross, right? If it touched, it would flatten. Okay? So it has to cross. And notice we ended at the lower right. Is that what we wanted to do? Should it have ended on the lower right? Yeah, it was the end behavior we came up with, right? If you started in the right place and drew it correctly as you went from left to right, you should end up in the correct place. If we would have ended up with it pointing that way, we had done something wrong along the way. So we know I need to go back and correct it. And if you plot this on a graphing device, you may have to zoom out and shift some things around, but you should see this shape. I mean, I might have to zoom out in the vertical direction pretty good, right? Because of this, how far down it goes. But you should see this. This is the whole point of doing all this. We got a pretty accurate representation of what this function does just by looking at zeros and multiplicities in a y-intercept and in behavior, right? All right, let's do the next one. Same concept. What do we look at for the degrees? The powers, right? Add up the exponents that you see on the factors, right? What do you get? 8, right? You got 1 plus 4 plus 2 plus 1, right? 1, 4, 2, 1. So the degree will be 8. Okay. Again, add the exponents. I'll write that down again so we're all on the same page. Add the exponents on the factors. What about the leading coefficient? 4. Again, notice that in all of the factors, the coefficient is 1, right? So at the end, we multiply by 4. If this were, say, 2x plus 3 instead, you'd have a leading coefficient of 8. Because you'd have a 2x in that first term times the 4. All right, so leading coefficient is 4. All right, so this is where we get to end behavior. Degree is even, so tails same direction or opposite direction? Same, right? Leading coefficient is positive, up or down? Up, okay? So now we need to write that as math symbols. So as x goes to negative infinity, f of x goes to positive infinity, right? As you go to the left, the function points up. As x goes to positive infinity, f of x goes to infinity again, right? As you go to the right, the function goes up. So far, so good? Okay. Y-intercept, how do we find that again? Yeah, put the 0 in for the x, right? Do f of 0 So when we put 0 in, basically it just makes the x disappear, right? So you get negative, you get a 3 times a negative 2 to the 4th times a negative 5 squared times a negative 8. If you're typing these into your calculator, make sure you have the parentheses around the negative 2 before you do a 4th power. Your calculator, if you don't put the parentheses, your calculator will do the power and then the opposite. Okay? Again, I'm not doing this one in my head. Negative 38,400? Yeah. What you got? What you got? Okay. If you write out your work and accidentally type something in your calculator wrong, that's not going to be a big error on anything. All right, what about the x-intercepts? What do we look at? Yeah, the y, yeah, we look at the f of x is equal to 0. And again, since it's already factored, we can see that easily, right? What do you have? X equals... Good. Right? Set each factor equal to 0. Solve for x. Just have to move all the constants to the other side. Again, for these two parts, we're talking about intercepts. So we should identify the points that are on the graph. So for part D, what points on the graph? 0, negative 38,400. And then for part E, what points are on the graph? Good. Again, intercepts are points. Points are described in order of pairs. But the bigger issue is we want to try to get a graph at the end, so I want to make sure that you understand these are actually points on the graph that we're going to use to help us draw the graph. All right. For part F, it asks for the multiplicity of each 0. For negative 3, what's the multiplicity? 1. Good. For x equal to 2, 4. For x equal to 5, 2. And for x equal to 8, 1. Good. And again, that we use the multiplicity to tell us two things, right? The multiplicity tells us flatten or not. It also tells us cross or touch, right? Those are the two pieces of information we're going to get. Okay? All right. Let's write down the first one, the flatten or the flatten or not. Where does it flatten? What tells you if it flattens or not? So, yeah, we got to be a little bit careful. Even tells us what? Oh, we just touch, right? Yeah, so it's just if it's greater than 1. So where does it flatten? At 2 and 5. Those are the places where it flattens. Doesn't matter if it's odd or even. Just is it bigger than 1, right? That's where flatten. The odd or even is the cross or touch. Okay. All right. Looks like we're ready to graph it. Let's see. 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8. Not looking for perfection. We're looking for rough sketch. Literally rough. Okay. And what else did we have? It was negative 38,400. Okay. So we've got a point at negative 3, 0, 2, 0, 5, 0, 8, 0, and 0, negative 38,400. So again, all this information gives us 5 points on the graph. We want to make sure we go through all 5 of those points. The end behavior tells us where to start. Do we start upper left or lower left? Upper, right? Upper left, yes, correct. Sorry. All right, upper left, come down to this first 0. Does it flatten? No. So if it doesn't flatten, it's going to go straight through it, right? It's also odd, so it has to cross. So we're going to go straight through this one. No flattening. Get down here. I need to turn around and go up to this one. And again, it's not going to be perfect. It probably doesn't turn around right on the y-axis, by the way. But we're just getting a rough sketch. Okay, that's the whole idea. It just needs to. We're just trying to get the big picture. We're not looking for the fine details. Okay. Up to the next one. Does it flatten? Yes. Does it cross it or touch it? It just touches, right? Because it's even multiplicity, right? Multiplicity is 4, so it just touches. So it turns around. Goes up, touches, turns around. Comes back up to 5. Ooh, that was ugly. Comes back up to 5. Flatten at 5. Yep. Does it touch it or cross it? Touches these again, right? Because it's even. Right? That multiplicity is even, so it touches it again. Finally, the last one, does it flatten? No. So we just cross right through. Does it end up in the correct spot? Should we have ended up in the upper right? Yeah. Yeah, because they were both tails were pointing the same direction. Is that okay? All right. You will have a problem just like this on your test next week. We have a test next Friday. I had to look at ahead of the schedule. We have a test next Friday. I promise you there will be one just like this on the test. All right. Well, let's go on to some new stuff then. Like I said, there's lots and lots of information we can get from the graph, particularly when we have it factored. So what we're going to concentrate on the next couple of sections is how do we get this factored? So before we talk about factoring things, we need to talk about dividing things. So that's what today's topic is talking about how we divide one polynomial into another. I'm going to remember to give you one this time. There you go. All right. So, all right. So we're going to talk about dividing one polynomial into another. And the idea is going to follow along the same lines when you're talking about dividing one number into another. Both of these are called what are referred to as the division algorithm. We're going to write down what the statement is. We're not going to worry about trying to prove it at all. But when we think about division algorithm, it's really going to be what we're doing with examples later on versus what we have up here. But what the division algorithm says is that if I want to try to divide one polynomial by another, so if I divide f of x by p of x, I'm going to get a piece that's a quotient and a piece that's a remainder, just like when you do with numbers, right? So for example, if you divide 15 by 6, you get a quotient of 2 and a remainder of 3, right? But when we're talking about quotients and remainders for polynomials, they won't be numbers. They will also themselves be polynomials, okay? So what we say is that there are, or there exist, polynomials, and I guess I should also say unique polynomials, q of x and r of x, such that we write this in what looks like a weird way, because I'm not actually going to write it as a division. But we're going to write it as f of x equals p of x times q of x plus r of x. So the q is the quotient and the r is what's left over. So for an example, when I just said when we did 15 divided by 6, we got a quotient of 2 and a remainder of 3. That would mean that I could write 15 as 2 times 6, quotient times 6, plus 3, plus the remainder. Okay, so it's just written in a slightly different form, but it's the same kind of idea. Well, think about when you did long division when you were in grade school. How did you know when to stop? If I take 15 and divide it by 6, I said it went into it twice, you'd subtract the 12 off, you get a 3. The 6 doesn't go into the 3, right? The remainder was smaller. That's when you knew how to quit, right? Well, with polynomials, to don't know when we quit, we have to look at a degree of an idea of something. So when we look at the r of x to know when to quit, we need either the r of x is 0, so it evenly went into it, or the degree of the r of x is less than or equal to the degree, not equal to, less than the degree of q of x. We know when to stop when our remainder polynomial has a smaller highest power of x than what we're dividing by. I know it's a lot of words, a lot of symbols, it's very confusing. I'm not going to make you write this down. I'm going to do it with actual examples here. And so as we go through more examples, it'll make more sense. Okay? I promise. All right. So let's do this first example. I want to divide the x cubed minus 3x squared minus 5, or excuse me, minus x minus 5 by x squared plus 2x plus 7. Okay. I want to start this off and write it just like I would write it back in grade school. I want to take the x cubed, let me write that down a little bit farther. The x cubed minus 3x squared minus x minus 5, and I want to divide it by x squared plus 2x plus 7. Kind of how you write with scaffolding in grade school when you're doing a long division. You know, call it scaffolding. That's kind of the technical word for it. Right? Should remind you of grade school just with letters as opposed to numbers. Right? Okay. In some regards, even though it looks more confusing, I think that dividing polynomials is easier than dividing numbers. And here's why. At any given stage, I only need to look at the leading terms of what I have left. Okay? So what I mean by that is, I need to say to myself, what do I need to multiply x squared by to give me x cubed? X. So that tells me how many times x squared goes into x cubed. Okay? So x goes up here. It's not, this part shouldn't be too difficult to figure out, because all I need to keep track of is my coefficients and my x is all. Okay? Now, what did you do when you did this back in grade? Let's do a slightly larger number. Maybe I wanted to do 9 into 587, say. You looked at this part and said 9 went into that 6 times. What did you do with the 6 and the 9? You multiplied them, right? And then subtracted. We're going to do the exact same thing here. I said x squared went into x cubed x times. I want to do that multiplication next. Okay? X times x squared gives me x cubed. X times plus 2x gives me 2x squared. X times plus 7 gives me 7x. Do the exact same thing that you do with numbers. And then subtract. Yeah, exactly right. We'll subtract. Now we have to be a little bit careful. And this is why I put a circle around my minus. This minus applies to everything here. Okay? So make sure that when you do the minus, you subtract each of the terms, right? It'll flip all the signs. Okay? X cubed minus x cubed gives you 0. Negative 3x squared minus 2x squared gives us negative 5x squared. Negative x minus 7x gives us minus 8x. Okay, we subtract, just like we did before. Okay. Over here, when we subtracted, what'd you do with the 7? You drop it down, right? Guess what we're going to do with this minus 5? Drop it down. Yes? When we subtract, I have to distribute the minus sign to every single term. Yeah, so that's why it was negative. Yep. If it were a negative, the minus would make it a positive. Yep, I have to subtract the whole polynomial off. Okay. Now again, when I do the next step, I just need to look at leading terms of what's left. What do you need to multiply x squared by to give you negative 5x squared? Negative 5. So we'll put the negative 5 up here. Take your negative 5 and multiply it through. Negative 5x squared minus 10x minus 35. subtract again like we did before. Negative 5x squared minus the minus 5x squared goes away. Negative 8x minus a minus 10x gives us what? Positive 2x. Negative 5 minus a minus 35 gives us positive 30. Okay. Over here again, if I were to finish off my example with the numbers, I know here I quit because my 1 was less than my 9 and there was nothing else to bring down, right? Agreed? Okay. I know that I'm done here because what's the power on what's my leading term here? It's x to the first, right? What's my leading term here? X squared. This is smaller as far as the degree goes. That's how we know we're done. Okay? So this is the remainder. Okay? Does that make sense? That's how we know we're done. Now, there's a couple of ways we could have done this one. This one's written to us as a fraction. So over here, if you were trying to redo 64 over 9, oops, not 64 over 9, 587 over 9. That was 64 was the whole part, right? And then you would have a 1/9 left over. And you wouldn't, if you wrote it as a mixed number, you wouldn't put the plus 1/9. You wouldn't put the plus sign, right? But that's what a mixed number means, right? We're going to write this in a similar fashion since we have it as a fraction. So over here, we have x cubed minus 3x squared minus, x minus 5 over x squared plus 2x plus 7. X minus 5 is the quotient. That's like the 64 over here. And then we would write plus the fraction piece that's left over. Okay. So it's quotient plus remainder divided by what we divided by. Okay. And it's like that up in the upper right-hand corner. That x minus 5 is like it's the 64. And this part is like the 1/9. Okay. We're going to do more examples, but any questions on this one? Is this okay? Do another one. Let's do the next one. Pardon me. We've got 6x to the 5th minus 8x to the 4th minus 10x squared minus 5 all over this 2x cubed minus 4x squared minus 2x minus 7. This one's a little bit different, not in how we're going to attack it, but notice in my numerator, I'm missing a couple of terms, if you will, right? There's no x cubed term, there's no x term. To keep your scaffolding straight, to make sure you've got all your vertical columns lined up nicely, I would encourage you, where there's a missing term, to put a 0 times x to that power, okay? So what I mean by that is, underneath my little division sign, I'm going to have a 6x to the 5th minus 8x to the 4th plus 0x cubed minus 10x squared plus 0x minus 5. Not only do I think it helps you keep things straight, there's going to be another division process we're going to do here in a little bit, probably on Friday, that's going to require you to put the zeros in when you need them. Okay? So I would encourage you to put the zeros in now so that you get used to doing that. Okay? This will be divided by 2x cubed minus 4x squared minus 2x minus 7. Might take a little longer to write out, but again, I think once you get the hang of it, polynomial division requires less thought than doing integer division, right? Because I only need to look at the leading terms, and I just need to think of what do I need to multiply the leading term of this to give me the leading term of that, right? So what do I need to multiply 2 by to give me 6? What do I need to multiply the x cubed by to give me x to the 5th? X squared. So what am I going to write up at the top? 3x squared. And notice I typically write it over where that term is in the polynomial we're dividing into. You don't have to, but it makes things line up nicer. Okay. Again, that 3x squared comes from 2 times 3 gives me 6. X squared times x cubed gives me x to the 5th. That's where that comes from. What do I do with the 3x squared now? Multiply the whole thing, right? 6x to the 5th minus 12x to the 4th minus 6x cubed minus 21x squared. This is why I said it's nice to have that 0x cubed term in there. Now I've got things lined up vertically, don't I? If you didn't put the 0x cubed in there, your minus 6x cubed would be under your x squared. Your 21x squared would be under the x term. It would look ugly. It would also be confusing, I think. What do I do now? Subtract. Leading terms go away. What do we get for the x to the 4th term? Get 4x to the 4th. Good. The x cubed term will be plus 6x cubed. The x squared term will be plus 11x squared, right? Remember that minus sign has to get distributed to everything, right? Yeah, well, yeah, that's the polynomial we're subtracting off. So yeah, it's just the second one that we're distributing into everything. Yep. So far, so good? Yes. You can do that if you would like, yeah. Yep. You can flip all the signs if you want. Okay. What do we do next? Yeah, but yeah, brought the 0. I'll just bring everything down. Doesn't matter. Just so we can keep track of everything. Now, what was the next question we need to ask ourselves? Good. Yeah, I need to look at the 2x cubed and the 4x to the 4th, right? What do you multiply 2 by to get 4? 2. What do we multiply x cubed by to get x to the 4th? X. So up here I'm going to write plus 2x. Good. It's a lot easier to figure than figuring out something like how many times does 23 go into 387. Right? Think about what you do in grade school with long division, right? It's a little bit easier to think about what do I need to multiply 2x cubed by to give me a 4x to the 4th. At least I think that's easier. What do we do with the 2x now? Good. Multiply by everything that went into that first polynomial, right? The one that we're dividing into or dividing by. 4x to the 4th. What's the next term? Good. Next term. Good. Next term. Good. And then we subtract. Good. And if you want to, you can flip all your signs at that point. That's fine with me. It doesn't matter. That's why I put the circle around the minus. It reminds me to distribute the minus to everything. Whatever you need to do to remind you that you need to make sure you're subtracting every single term, that's what you should do. Okay. All right. What do we get when we subtract now? Good. Yep, exactly right. So the 6x cubed minus a minus 8x cubed gives us the 14x cubed. 11x squared minus a minus 4x squared gives us 15x squared. 0x minus a minus 14x gives us a plus 14x. And then we drop the minus 5 down again. We haven't done anything with it yet. Is okay? Last part. We're almost done, right? We've got the powers are equal now, so we're almost done. What are we going to put up here at the top? Plus 7, right? Yeah, 2 times 7 will give me 14, and the x cubes already match, right? So we get a plus 7. So we distribute the 7 through. We get 14x cubed minus 28 x squared minus 14x minus 49. If I did my multiplication correctly. 15x squared minus a minus 28x squared gives us 43x squared. This one, because this is why I said make sure you keep track that you're subtracting everything, right? It looks like these might cancel, but 14x minus a minus 14x actually gives us positive 28x, yeah. Negative 5 plus 49 gives us plus 44. And again, what tells us that we're done? Yeah, that power here is smaller than that power there. Exactly right. The squared is smaller than the cubed, right? So we're done. So doing this just like we did the last time, if I have my 6x to the fifth minus 8x to the fourth minus 10x squared minus 5 over 2x cubed minus 4x squared minus 2x minus 7. What do we write first? Good. Write the quotient first, the 3x squared plus 2x plus 7, and then plus, what's next? Good. This denominator here should match this denominator over there. Okay? When you write the fraction as you divide it. The denominator that's on the left should match the one that's on the right. Okay? So again, this part is your quotient. This part is your remainder. What questions do you have on that one? That process okay? So what I would like you to look at for Friday are the next two problems. Hopefully they'll be a little bit even quicker because we just have an x minus 4 on bottom and an x plus 1 on bottom for those two. Look at those two problems for Friday. See if you can follow the same pattern. Okay? We'll do those first on Friday, and then we'll talk about a different method to do those a little bit quicker. Okay? All right. So see you on Friday. Have a good one.